everybody. Thank you again to be here with us for this next seminar of our cycle, the research of our future. This morning we have here Roger Courcoy. He started the PhD last year in the DRM group of our institute. Roger has a long experience in research, particularly related with the measurement in the atmosphere of greenhouse gases and tracer such as the radon. Roger worked already in the Barcelona University, in the Climate Institute of Climate Science, and in the Autónoma University of Barcelona. And he joined us last year to start his PhD. So thank you, Roger. You can start whatever you want.
Okay, hello everybody. So my presentation will be about the radon atmospheric measurements and the application of the modalities of the environment monitor. So I will begin with an introduction about climate change and the need of the improvement of the greenhouse gas verification tools. I will introduce the radon tracer method and projects related with this methodology, and finally I will introduce the new ARMON monitor that we are doing here. So first of all, for numbers that well now everybody must already know. Climate change is real. Models demonstrate that it's a human force. So up to now, it's about 1.1 degree of surface temperature increase since pre-industrial times. The two cases more that affect more to this increase are known to be carbon dioxide and methane. According to the last intergovernmental panel on climate change. So looking at what's happening in the atmosphere, for example, CO2 have risen from 300 to more than 400 up to 420 ppm in the last decades. And we see what's happening with methane. It also rise from pre-industrial times, from about 700 to more than 1800 ppb. So where does these gases come from, and where are they going to? Most of these gases are coming. Looking at CO2, most of this CO2 is coming from burning fossil fuels, and there's about 11% of this increase in CO2 emissions that are due to land use change and forests. And where do these CO2 go? So about 48% remains in the atmosphere. There's 29% that sinks, that actually sinks in the land, so that's land take, and about 26% of ocean. These figures are well. This is a figure quite new from the Global Carbon Project, and I remember I've been for more than 10 years in this field, and you can put the other.
Yeah.
No, the last one.
Ah, sorry.
No.
Oh, no.
Yeah. This 29% 10 years ago was 53%, and also this 26% that remained that was sinking in the ocean was more than 50%. So there is every day less capacity of land uptake and ocean uptake of these gases. About the methane, here we can see what are the main sources. Here we see anthropogenic sources, but also natural sources of methane. Anthropogenic sources are waste and fossil fuel production. Natural sources are wetlands and waters, termites, but this is called number. So looking at this problem, there's a need for an ambitious code of these emissions, and there's a need to know exactly the number of these emissions, because nowadays these emissions are commonly estimated and reported by each national agency to the United Framework Convention on Climate Change, but there are still lots of uncertainties. There are still lots of uncertainties in carbon dioxide emissions, in methane emissions. So this need to understand exactly which are the numbers. So how we estimate these greenhouse emissions? To some years ago, there were two main ways. First, there were top-down methodology, which is getting the data from observations, getting the data from atmospheric stations, and using models to convert these atmospheric concentrations into emissions, based on national inventories with low resolutions, using these atmospheric measurements and models, trying to get those solutions. And the more used way is the bottom up, which is just getting data from inventories and fossil fuel consumption and proportionate activity data. In this last COP26 conference, there was an announcement by Copernicus of a new independent verification tool, which will be a mix of these two methodologies. We'll get data from observations, we'll get data from inventories, and we modelize, and as an output, it will give the real data in very high resolution. But for this model, it's needed to have good atmospheric measurements and good emission inventories. And in this field, there's the Radon. Why the Radon can be a tool for having much more information about these emissions. Well, radon is radioactive. It have a spectrometry. It's natural radiation. So it's coming from the behavior of radium. It's low mass, so it has no chemical reaction or nuclear deposition. It has a half-time of almost 4 days. There's no installation where it can be taken as zero over the ocean, And well, that's quite insurance process, but it is not really true, but we can have a good match of fluxes. So all these characteristics of radion utilization tell them to be a good ratio for a good ratio for other gases. It's radion has been used, for example, in studies of bond divider to as there is a regular emission, we can know how the air is mixed or not well mixed in this bond divider. And since some years ago is also used with the radion pressure. I will explain a bit of this methodology. It's a box model. So it's assuming the stable bond divider. For this case, we can only be used during the night when we suppose the bond divider is stable. And it also it's also assuming regular radiant flux over these box over this area. So we it's getting this methodology is getting one time the radiant flux. There are maps of radiant flux. And these maps are being improved to have better resolution, not just better resolution in space, but also better resolution in time, because the radiant flux is not regular all the time, but it changes depending on many factors as soil humidity, for example, or temperature. This methodology has been used in stations where we can get radiant data and another gas data, and it's used to get the flux of this other gas data. Mostly, it's being used on greenhouse gases in CO2 and CH4. But it's a methodology that I can use for other gases. So, so having the increase during a period of time where we consider stable the bond divider, as knowing the flux inside this box of the radion, and knowing also the increase of the target gas, that could be CO2 or CH4, we could easily get the flux of this other target gas. Well, with Claudia, we use this methodology in station in Gredos, which is in central Spain. We use this methodology, but we improved with the use of back trajectories. So we were not just getting the box, but we were getting the real surface where the air was coming. These back trajectories are simulations to know whether the arriving station has been in the past hours. So using this back trajectories coupled with the radiant trace model, we could estimate the fluxes. In this case, it was methane fluxes around the station. What was interesting in this study is that we compared these fluxes with inventories. There's an methane inventory called Edgar, which gives Michigan estimates of methane for Europe. And what we could see is that during some months, the observed fluxes of methane were similar to the inventories, but in some of the months, the inventories really much larger emissions than observed months. So what was happening here? Well, this site was characteristic because of transparency. So there were some months that it comes and some months without goes. And what we could see is that the months where the codes were present in the area, the model coupled with the observations, the months where codes were not present in that area, the numbers disappeared. That was just an example of application. But in order to improve the radiant model application, we need high quality and harmonized radiant concentration observation with high spatial resolution, reliable radiant flux inventories with high spatial and temporal resolution, and standardization of the radiant methodology. There's a new, it's a 1 year running project, a European project that has these objectives. So first working package in this traceRadon project is to have traceable measurements of all the radiation activity concentration. So to have good atmospheric measurements of radon. Work package 2. The objective is to have good radon flux measurements. The result of the radon flux measurements, will be used to have better radon flux maps, which are needed for the radiant methodology. In work package 3, there's this validation of the flux models and services radiant flux and this project is also related to this network of atmospheric stations all over Europe. The quick idea is to have a radiant atmospheric radiant measurements in all these stations, all these European stations. So the radiant trace methodology can be applied in all of this network, and the idea is to have a unique methodology, traceable, and reliable. So up to now, last year, there were 3 main monitors capable of measure radon, atmospheric radon below 100 becquerels. the high-level monitor, the answer monitor, the ARMON monitor. The ARMON is the one that was developed here at INTE. So this monitor is based on polonium collection at a detector inside detection ball, inside the sphere, which is charged. This was charged to feed kilovolts. So charging particles of polonium concentrating, which is a descendant of radon. It's calling detector. And there's the peak detector detected the alpha decay of these at this point 118 particles, which were the main characteristics of this instrument. So online full alpha spectral analysis, it could be used remote control. It also had measurements of thoron, which can be interesting in these applications. It had portable dimensions, and the response was not influenced by the atmospheric up to 6 ARMONs were bought with different efficiencies from 0.3 to 0.4. And the minimum detected concentration was 200 millibecquerels per. The instrument was calibrated in each radon chamber, which is traditional German national intelligence. This instrument was previously compared with other instruments. The other instruments I presented. There was this paper of Claudia with this intercomparison, which agreement was found between most of them. Well, there's more information on the paper because some other instruments have problems in reading evidence. Well, the paper of Claudia, it's well explained. So the idea of my PhD here was also to improve this equipment, to make it more robust, to make it more user-friendly, and also trying to improve the efficiency, So in the frame of 2 projects, one the traceRadon that I have already told, and the second one is the Maria project, which was a project by the Generalitat de Catalunya, and with the objective of this prototype building, well, we produced this new ARMON instrument. This ARMON, this new instrument should have the parameters regarded in the traceRadon project, which has to work in a environmental temperature of -25 to +50, with environmental relativity from 100. Also a range of pressure. It should be capable of a response from 1 to 200 per kilometer cubic with a sensitivity higher than 0.3 and a total uncertainty less than 20%. Okay. about. So first, it was theoretically designed a new detection bureau to improve the efficiency and like the film. And also, it was designed the structure of the instrument and position of every equipment and how we could control all the sensors and the high voltage of the instrument. So it was in frame of Maria project. And in the frame of the traceRadon project, we did this LabVIEW program with monitoring the radon and also monitoring all the other parameters of the air that is coming to the instrument. For example, the flow, the water concentration, and the temperature. It controls the voltage applied to the detection volume and monitors the radiant concentration. The instrument was installed in a flying box case of 50 by 50 by 150 centimeters. In the lower trays, we put the high voltage, the volume detection volume, which is this spare, and the detector. Here there is the amplifier, and in the upper trays, we put the sensors, the electronics, and the multi-channel analyzer, and the laptop to control everything. We calibrated the instrument in the chamber, radio chamber. We had some problems at the beginning because depending on the position of the detector, we get different efficiencies. The end, we think we reach a stable position of the detector where we get an mean efficiency of 0.55. You observed what was happening at low concentrations, and we compared the response of the instrument to two commercial radio monitors. We observed that, well, that's what was something that we knew the stability of the ARMON was much higher than these other instruments that are not working in low concentrations, from 0 to 200 becquerels. We know that the efficiency of the instrument is affected by water presence, water vapor. High humidity lowers the efficiency because it reduces the number of particles of pollen that reach the detector. But we have a quite good agreement in this correction, water correction from 0 to 2000 ppm. Well, for more than 2000 ppm, the correction is not pretty good, so we do not recommend to use this instrument open. Yeah. So there's a need to dry the air that's coming to us. We compare the response of the new instruments to no ARMON as places in the group. The agreement was this that was during June 2021. There was a good agreement between the both instruments and with the higher efficiency of the new instrument. During this intercomparison, we found some polonium 260 cones, polonium 200, well, cones which were quite surprised because they were not following the same cycle as the Radon, well, the polonium 280 cones. So we decided to make background check what was happening in the instrument where zero error was coming to the instrument, and what was happening in background conditions. So we put zero error to the instrument from a tank. We could see that all cones were coming to zero. And then we introduced silica gel, and what we could see is that there was here there was the red, here we introduced silica gel, there was an increase in polonium 200 and polonium 280 counts. These counts is affecting the total uncertainty of polonium 280. So lots of these counts are introducing more uncertainty on the radio measurements. So we want to avoid these counts, and well, there was a surprise that there were coming counts from silica gel, but for the final design of the instrument, we decided to introduce, well, first we tested the 7-liter buffer. When we put the 7-liter buffer after the silica gel, we saw a reduction of these counts up to zero. So in the end, what we decided is in the final design of the instrument, the final design of the drying system, because as explained before, we need the air to be dry. We introduce a 10-liter buffer tank to cope with these undesired cones that are coming from the silica gel, which was a surprise. Finally, we make a user manual on this instrument for people who's going to use it. And within the frame of that regional project, we extend the instrument to PTV for an intercomparison and complete calibration. And the instrument will also go 6 months at night station, exactly for a 6 months intercomparison. So to sum up, well, the utility of the rate person method in helping the improvement of greenhouse gas emissions calculus implies an importance of standardized this methodology. The research collaboration, which is the traceRadon project, is analyzing all this data and comparing the response of different atmospheric radiant monitors. New one monitor for radiant concentration has been built and tested at PT laboratories, and this instrument will be used as transfer standard project. Tests have demonstrated that silica gel can be a source of may cause an increase in the total uncertainty of low rate of measurements with ARMON. So the need of introducing a buffer. And finally, that atmospheric rate of measurements are being carried out within the development of network. ICOs, and it will be important to have as many stations as possible, to have as many data as possible of radon, of greenhouse gases, and complete radon and greenhouse gases to have plus data as much as possible. So thanks for your attention. Well, it's presentation. All this work has been done with for all these people with Claudia. Thank you.
Thank you, Roger, for the presentation. If there is anybody in the room that will make some question to Roger, please.
Yes, can I ask?
Yeah.
Thank you for among different things for improvement of the ARMON sector. You mentioned that you managed to achieve, if I understood well, a better distribution of the electric field, electrostatic field inside the sphere. Could you explain some details of what exactly have you improved and how?
Well, the old instrument, it was not a regular sphere. It was sphere, but at this point it was there were the detectors, and now the sphere is more regular. For the sphere. So the electric field is also more regular inside the volume.
Roger, sorry, from the virtual participant, they are saying that the Yuri question was not properly listened. So if every time you can summarize the question.
Okay.
Yuri was asking which was the work done to improve the efficiency of the instrument before the old and the new version.
So changing the geometry of this sphere. Well, that's the fact that it was Claudia who did this. Used the console software, which there's a drawing of this here. But he compared the old geometry with this new geometry, and there was improvement in efficiency because of this improvement on the regularity of the electric field.
So this
Yes, this is metallic which high voltage at 8 well. In the old instrument, it was 8 kilovolts. In the new instrument, is you can get having 10 kilovolts, because now that we have a more regular geometry, we also can increase the voltage.
So one electrode is the sphere itself, and the other one is where is the second electrode?
No, here everything here is charged and weight, and the detector is here, is at 0. Yeah, the detector is here, where all these lines are going.
I see. May I also ask other question? In the introduction,
Yes.
this was also very interesting when you have compared the sort of the distribution of CO2.
Yes.
You said that this gas ends up, and we took 3 pictures.
Yeah.
This here.
Yes.
But as far as I know, CO2 is consumed by trees, by plants.
Yes.
This
This
is where?
this
This
well, this is just the exit of CO2. I mean the anthropogenic CO2 emission.
Ah,
So in without anthropogenic emissions,
Mhm.
I mean, there were no increase in the atmosphere, so this number should be zero. And all the release from land and ocean will get also seen in land. So the increase in CO2, so the anthropogenic emission, where is going? So the one is capable of this to take this 29% of this excess of CO2.
Yes, I understand. Okay, thank you.
Any more
Any
questions?
more questions?
From the other side, is there any question?
Do you have any question from the remote access? No.
Okay, then I have one.
Arturo has one.
Okay. I would like just to ask from the RTM method,
Yes.
whether it's okay. So if you need a box
Yes.
and you can only use for nights, it's not a very. It seems a little bit limited in both in time and also in size. So how you will manage it?
Arturo is asking about the limitation of the RTM method, because this method so far can only be applied at night.
And also in a box, which also is a solution in the spatial.
Yes.
It's local.
So this is, and then we see maps from Europe and so on. So how are you going to
Of course, the rate interest methodology can only be used around the station, some kilometers around the station. So this box, depending on the zone, this box can be larger or smaller. In Germany, for example, this box is larger because the geography, as there are no mountains and the geography is more regular, we can think about a more regular space where both of the islands have the same limit. In places with where the geography is not so regular, this methodology needs to be improved. And I think the traceRadon also, well, at least I hope traceRadon project is also about this, trying to improve this methodology. Also using back trajectories, also using so the use of back trajectories as being in Grados. In fact, we are not using back trajectories. We're not using a regular box because we just get in the pixels where the air has gone. The pixels inside the box, yes, but we think of a grid box and we take the pixels where the air has gone.
So the idea is to improve this system with to see where the air is coming from, or at least from some period of time, and then apply the probability of this multiplied by some kind of radon flux. Or I mean,
yeah, I think the future must go that way.
Okay.
For moment it's a simple methodology, but I think that needs to be improved. It needs to be more studied. I hope the rerun project will focus on this also. No, well,
Yes, no, Roger's right. Actually,
but
I
think that there's a need to improve the methodology, but because that's it, it's methodology that in some stations can work very well. in stations where no without a lot of geography incidents as mountains or coastal zones, because this box works really well. In other places needs to be studied.
Yeah, you have also to consider that the ICO station is formed by 100-meter tower observation. This means that the local is not so local because the cone of influence is much bigger, the footprint of the station. That's why they are interested in this. And the RTM doesn't want to be the unique method as an integration to validate and improve regional flux mappers. So also if you use it only at night, if you are able to validate the CO2 flux and you are modeling with other tools at night, you can assume that your model is working. That's why you don't have to think that the RTM is the solution. It's just an additional tool.
May I ask also a question related to this page? On this map of the radon flux, there are regions with different colors, yes?
Mm-hmm.
So the darker color means what the higher
flux.
higher flux, yes? Why then there are regions which are more blue or less, so to say? Is it related to some human activity?
No, it's related to the soil.
Only to the soil.
Yeah, it's related to the soil. Depending on the kind of soil, kind of rocks you have. So in Spain, maybe in the next there's a better radar map. I don't know. No, it's the same. It's the same map. So there are also in the Radon project there are working packages where this map is being improved. Yeah, it's depending on soil and also depends on BDG and other factors. But yeah, it's all this is natural natural.
You have the equation taking into account the soil characteristic and the weather conditions. Actually, the radon flux model as input, they use reanalysis of the weather models. Because in case of snow or rain, the exhalation of the radon from the soil will change. Related with the weather condition, the permeability of the soil, the capacity to filter or not the water. So the idea in the traceRadon is using real radon flux measurement to improve this model, which will be then used for the RTM application.
But in general, the soil is not working.
Yes.
There are no flux.
You have different kind of rock, but in general, yeah.
Usually it is proportional to the radium content, usually, but then it also depends from the porosity of the soil, the emanation factor, the length of the diffusion of the radon in this soil. You know, there are several parameters which are included in the diffusion.
Radon, which is uranium, so it's.
Radium is descendant of uranium.
No, radium is descendant of uranium.
Okay, thank you.
So, I think we can close this seminar. Thanks again, Roger, for this presentation.
Thanks for your attention.
And I want to remember that we will meet again the 3rd of December with Alejandro Cifuente. He is from the NEMEN group, and he will give us a presentation simulation development of a catalytic membrane reactor for hydrogen technology. So thank you. See you next in 2 weeks, Friday.